Assalamualaikum students, welcome to our second lecture. In this lecture, we will study about one more example of a simple harmonic motion, which is motion of a simple pendulum. So let's start. So a simple pendulum, it also exhibits the simple harmonic motion. So here's an example of a simple pendulum. Like you can see, there's a small bob whose mass is m. It is suspended from a light string of length L. This is the length of the string, and at its upper end, so it is hanged from its upper end. Now O is basically the point. This is known as the mean position, or you can also say it as equilibrium position. And this is the point where a whole weight of the bob, whose mass is m, is acting. And as we know with the formula that weight is equal to mass into gravity, and this is known as an equilibrium position or a mean position. So O is basically the mean position, and the mean position is basically the position where there is no net force which is acting on a bob. This means our bob is stationary, it is at rest. Now you can see two more positions here, position A and position B. These are known as extreme positions, and in these positions the net force is not zero. This means there is some kind of net force acting on position A and position B. So you must distinguish between the positions O and position A and B. Like the position O, there is no net force, and position A and B, there is a particular net force acting on it. Now there are two components of the weight which are acting on the bob. So as we know, like when we decompose our vector, like our vector is like weight which is acting in downward direction. So it is composed in two components, horizontal components and vertical components. So we have two components such as mg cos theta and mg sin theta. Now if you look, there is no force acting along the mg cos theta component because there is a tension known as, this is T, this is tension in a string. The tension in a string cancels the component of the weight mg cos theta. You can see here the mg cos theta sign, the arrow sign is acting in downward direction, whereas the T, the tension string, is in upward direction. So these two components cancel each other. That's why we don't have mg cos theta component right there. Now the other component mg sin theta, it is acting along the mean position because it is moving towards the mean position, and as it is moving towards the mean position, so it acts as a restoring force. And we discussed last time that the restoring force, it always pushes or pulls the object performing the oscillatory motion towards the mean position. So the restoring force pushes the bob towards the mean position. So you can see that due to the restoring force, the bob moved towards the mean position. Now when the bob moves from point A towards the point O, which is the mean position, it has a maximum velocity, and due to its maximum velocity, it does not stop at the mean position O, and it moves towards the position B right there. Now when it moves, now it has a maximum velocity at point O, but when it moves from point O to point B, like in this direction, then the velocity of the bob decreases. Now after some time, when our bob reaches at point B, the velocity of the bob becomes 0. But as the restoring force, because the restoring force is acting in both directions, like at position A as well and position B as well, so the restoring force still acts towards the mean position. Therefore the bob again start to move from position B to position O. Hence there is a continuous motion, to and fro motion from of bob from position B to position O, then A, and then again it comes back towards the position B, and this continuously moves on. So our bob, it continues the to and fro motion about the mean position O. Now one important point here is, like, the speed of the bob increases while it moves from point A to point O, and it is, as we discussed, due to the restoring force which acts towards the point O. Therefore the acceleration of a bob is also directed towards the mean position O. On the other hand, the speed of the bob decreases when it moves from point O to point B, and this is again due to the restoring force, and the restoring force always act towards the mean position. So the acceleration of bob is also directed towards the mean position. So you can see in both cases the acceleration of bob is always directed towards the mean position, and this is the basic definition of a simple harmonic motion. We have last time discussed that a simple harmonic motion, the object is always directed towards the mean position, like its acceleration is always directed towards its mean position. Hence we can say that the motion of a simple pendulum is a simple harmonic motion. Now, let us look at the time period of a simple pendulum. So, the time period of a simple pendulum is given by t is equals to 2 pi, then square root L over G, where L is the length of a string and G is the gravity. So, the time period of a pendulum is basically the time to complete the one cycle. Like you can see the arrow, like let's say it moves from point B to point A and then it again comes back to point B. So, this is one time period. One more important thing is that the time period of a pendulum is independent of its mass and amplitude.